This is FRQ number 1 from the Dynamics Review Packet. It says that two guide rails for the elevator shown above each exert a constant frictional force of 100 newtons on the elevator car when the elevator car is moving upward with an acceleration of 2 meters per second squared. The pulley has negligible friction and mass. Assume G is equal to 10. And on the diagram, draw and label all forces acting on the elevator car and identify the source of each force. Well, if I'm looking at this elevator car right here, there's got to be an upwards tension force. There's a string, and it's accelerating it. So there's a tension force going up. There also is two frictional forces from each of the guide rails. I'm going to call that frictional force F1 for the guide rail on the left, and I'm going to call the guide rail on the right F2. And then there's also the weight mg of the elevator itself. So there's my free body diagram. I haven't really scaled it well. The tension force should be a bit larger than the way that I drew it because it's moving upwards and accelerating. So the tension force is going to have to be larger than the combined others. When I write my dynamics equation in part B, I'm going to recognize that the sum of the forces in the y direction is not equal to 0. And the reason that I know that is that it's accelerated. So I'm just going to write kind of my free body diagram out as an algebraic expression. It's going to be Ft, which is positive, minus the weight of the elevator mg, minus F1, which is the frictional force from the left guide rail, minus F2, which is the frictional force from the right guide rail, is equal to F net, or my leftover force. Solving this for Ft isn't that bad. I'm going to add everything over to the right-hand side. I'll make a few substitutions. For starters, I'm going to substitute Ma for F net. This becomes Ma, and then I'm going to add to it Mg. And then for the two frictional forces, since they're the exact same, they're symmetry, I can just say it's 2 times, the 100 newtons of friction. Or you can just write it as plus 100 newtons. That's fine. And then I'm ready to go. Well, the tension force is equal to mass times acceleration. Well, the mass of the elevator car is 400, and it's accelerating upwards at 2. So 400 times 2 is 800 newtons. So the net force is 800 newtons. And I'm going to add that to the weight of the elevator. They told us to use G. So M times G, 400 times 10 is 4,000. And then to that number, I'm going to add 2 times the frictional force of 100 newtons. It appears as though I left the newtons off of the weight there, so I'll add that in. So now I have 800 plus 4,000 plus 200. And my tension force then, when I add those all up together, is going to be equal to 5,000 newtons. And the direction of that, of course, is up. And that's my answer to question part B. Then they go on to say, calculate the mass that the counterweight must have to be in order to raise the elevator car with an acceleration of 2 meters per second. So in this problem, we need to recognize that there's the string here is attached. So the downward acceleration of the counterweight is going to raise the elevator. If there's no motor, this is just gravity kind of running this whole machine, then I can say that the weight of the counterweight mg minus the tension. So I'm calling anything that moves in this direction positive. So I need to kind of unify my coordinate system. That means that on the left-hand side we called upwards positive and downwards negative, and on the right-hand side we're going to call downwards positive and upwards negative. That means mg minus ft is equal to F net, which eventually I'm going to replace in this next step. I'm going to replace that with MA. So mg minus ft is equal to F net. Now I can solve this for ft by adding ft to both sides and subtracting F net from both sides. that becomes m times g. When I subtract Fnet, I'm going to replace it with Ma. Now, that's the mass of, this should be a kind of a capital M, that's the mass of the counterweight times the acceleration of the counterweight. And on the right-hand side, I'm going to have the Ft that I added to both sides. And then I can, and the reason that I did that is because I want to isolate the variable m, and I want to factor it out. In this case, I have m times g minus a. So now I've factored out the size of that counterweight, and I know what Ft is. Ft was solved for in part B. It's 5,000. And so g minus a is 10 minus 2. Both of these are also known. And so 10 minus 2 is 8. And I can say, therefore, that m, when I'm kind of all said and done, is equal to 5,000 newtons, which is the tension. 5,000 newtons. And I'm going to divide that by 8 meters per second per second. And my answer is going to be in kilograms. By the way, a newton is a kilogram meter per second squared. So a kilogram meter per second squared divided by a meter per second squared is just a kilogram. When I divide 5,000 by 8, I get 625 kilograms. So if there was no electric motor in the system, and this were simply a gravity-powered elevator, there are a lot of reasons why that would not be useful. Try going in the other direction. But in this case, now we have our answer of 625, and that completes FRQ number 1.